Oh.
Any questions?
Are we starting a new chapter or anything today, or?
Yeah, that was the plan.
Okay.
Okay, that was it.
Just for my notes.
So sort of recapping, we started out with Coulomb's law, and then eventually that led to Gauss's law of electricity. That if I look at the electric flux over a closed surface, that's going to be equal to the enclosed charge over epsilon sub naught. So just Coulomb's law manipulated after manipulating with math and definitions. Then we have a magnetic flux through a closed surface, because you can't, especially in classical physics, you can't have a north pole without a south pole. Unlike charges where it could have a positive charge or a negative charge, this would be equal to 0. Then, looking at the magnetic field around a closed loop. So far we have mu naught I. Enclosed. When I say enclosed, if I have a loop of wire here, it's basically it's the current that's flowing through whatever the loop is. This was Gauss's law of electricity. Gauss's law of magnetism. Ampere's law. So the importance of these are 2.5 or 2 2/3 of what are generally called Maxwell's equations. Again, Maxwell did not call them that, someone else did. It turns out that there is a piece missing here, and Maxwell's going to contribute to that. However, we need to do a little bit more background in order before we get there. Introduce Faraday, I think Michael Faraday. He was playing around with circuits, 1820s, 1830s, somewhere in there. And so he had a loop here, some sort of power supply, and a circuit that can be made or broken just by flipping the switch. He had another wire over here, set of wires over here, hooked to an ammeter, a galvanometer, measures current. And what he noticed is that when he connected the switch, the needle on the galvanometer would flicker and then go back to 0 again. When he disconnected, the needle would flick in the other direction and then go back to 0. So you play around with this some, and you can actually get better results if you stick that secondary wire inside. But if you play around with it, eventually figures out that what's changing here, or figures out that it's the changing of something that seems to have an impact on the current here. Because when he connects it, the needle will flicker and then go back to 0. And when he disconnects, it flicks and goes back to 0 again. Well, when I make the connection, I'm generating a current. Suddenly I have a current, and then I disconnect, I lose a current. But the current generates a magnetic field. And what he figured out is that we are creating a current, the EMF, based upon the change in the magnetic flux with respect to time. I'm going to add something to that in a moment. Now, if I have this type of setup here, I make the connection, I create, suddenly I go from no magnetic field to having a magnetic field, so there's going to be a change. The magnetic field changes will create a voltage in this circuit, which creates a current, an induced current. Well, that induced current is going to create a secondary magnetic field. So we end up with the situation of there needs to be something else here, because the induced current creates an induced magnetic field that has to fight the change. Because if it bolstered the change, then suddenly I could create the circuit, creates a magnetic field, which then creates if it made the magnetic flux stronger, then suddenly I get an increased magnetic flux, which then induces another current, which increases the magnetic flux more, and we get this runaway power. So there's a minus sign here to indicate that the induced current will create a magnetic field that opposes the change in the magnetic flux. Faraday is usually credited with figuring out that there's a connection, and Lentz is generally credited with the minus sign. It is called Faraday's law. However, I think properly it should be Faraday-Lentz's law. Now, if I think about voltage, I know that voltage, the relationship between voltage and electric field is, so delta V is equal to negative E dot dx. Actually, the minus sign should be there for typical voltage. Minus sign is just going to magically go away in a moment. So we can now put this into a relationship like we have over here. That if I take the electric field around the loop, that's going to be equal to the negative change in the magnetic flux with respect to time. So we now have, and then Faraday-Lentz's law. So we now have almost all of Maxwell's equations complete. Almost. Maxwell hasn't actually made his appearance yet.
Is there another one?
No, there's something that's going to be tacked on over here. Just as a teaser, we talked about current in equals current out, which seems to make sense of whatever I have flowing in flows out, unless I have something storing charge. Then I have stuff flowing in and not flowing out. So if I take a capacitor, yeah, if I have a current flowing into here, I'll have a current flowing off the capacitor, but do I have a current really flowing off this plate? Because the rule was that if I have it flowing into a point, I have the same amount flowing out, but there's a gap here. Maxwell will figure out that gap. And then that will lead to, actually, relativity. All right, so a couple other things here, just background. So the electric flux is the integral of E dot dA. Magnetic flux. Okay, what is calendar work? That's better. And the magnetic flux. Integral of E dot dA. So let's take a look at a simple, what's called a motional EMF. A motional, not emotional. I'm going to take what I sometimes refer to in test problems as a U-shaped wire. I wasn't quite sure how else to describe it. Basically, I got a wire like that. I have a magnetic field. Before we finish this, who's seen The Princess Bride?
It's been a while.
All right, so
Some clips of it.
I'm gonna make a Princess Bride reference coming up here soon. So
I never liked that movie as much as everybody else did. Like, everybody's obsessed with that movie, and I never got it. Like, I've seen it like once or twice, but
have you seen it as an adult?
probably not.
Okay. We'll revisit it again.
Yeah.
Tastes change.
Well, I was never like into Monty Python as much as everybody else was either. Like,
You know, like Monty Python?
Oh,
Like the comedy sketch script or one of the movies?
the movies, like
yeah. That's not. Are you thinking?
like Holy Grail and
Yeah.
whatever the other.
I would not have lumped Princess Bride into a Monty Python type thing.
I don't know. It relates in my head somehow, or with the type of humor, I guess. I don't know.
All right. So, other than Phil, it is definitely worth watching. If you've ever seen Honest Movie Trailers, where he basically makes fun of every movie except for Princess Bride.
I'm not saying it's bad. I didn't think it was bad. I just was, like, everybody seems to like obsessed with that movie. Like, throughout my entire life, people talk about the movie.
All right. So I've got a wire right here, and I have a secondary wire sitting on top. So these aren't insulated wires, so I'm not having to worry about, there's a connection here. So in theory, if I put a battery in here, I could get a complete circuit pulling around. I'm not gonna put a battery in there, but for right now. I'm gonna make that dimension L, and this dimension here, W. So the area of this rectangle here would be LW. The magnetic field is B. And assume that it's uniform. Okay, so first off, what is the magnetic flux going through this loop right here?
Well, we know it's the integral of B dot dA, and we know that the area is just L times W.
Yeah, so the magnetic field is uniform here, so that can pop out. B dot integral of dA, so that's just B dot A. And so it ends up being, and I'm gonna make the magnetic field, or the area vector in the same direction as the magnetic field, which is tradition there. And so we end up with dA or dLW.
What happens to the vector signs?
Dot product is a scalar product.
Okay.
And since the magnetic field and the area vector are in the same direction. So now what I'm going to do is I'm going to take this wire and I am going to move it to the right at some speed v. So through some sort of magical powers, I'm going to move this wire. It's still on top of the green wire. So we still have a complete connection. If I should be able to create a voltage based upon Faraday-Lentz's law, that I'm not going to worry about the sign right now. The magnitude is d phi, which is ddt of my magnetic flux, dLW. Well, B is uniform, so it stays constant. L is constant, so they can just pop right out. dL dW dt. And dW dt is just the rate at which W is changing. In other words, V. So we're going to induce a voltage or an EMF in this wire here, given that magnitude. Now the question is, which way is the current going to flow? So first off, the Princess Bride reference, when West, I don't have any spoilers, so I'm gonna throw in here. Billy Crystal and Carol Kane were helping revive Wesley, and he says something which Billy Crystal says, to Blev, he said to Blev. And his wife says, no, he said true love. To Blev. I actually did say that everyone should watch Princess Bride in one class, and the extra credit on the last class was Princess Bride question. Anyway. Now the direction. As this moves out, is my magnetic flux increasing or decreasing?
Say that one more
So it's
time.
increasing.
I heard several voices and didn't understand any of them.
Say that one more time.
As the brown wire moves outwards, is my magnetic flux inside here increasing or decreasing?
Increasing.
Why?
Well, we know that it's BLV, and as you're gaining, like I guess the speed.
BLW.
Oh, that's
The flux.
Okay. Then it would.
Is W increasing or decreasing?
W is increasing.
Okay, so the magnetic flux would indeed increase because we're increasing the area. I could also increase the magnetic flux by changing the magnetic field or increasing the magnetic field, but here we're doing it by area. So as the area gets bigger, my magnetic flux gets bigger. So my induced current wants to oppose that. It wants to keep that from happening. So the induced current is going to flow that way. Because if my current flows that way, it's going to create a magnetic field into the board. So I'm going to have the secondary magnetic field into the board to try to reduce the rate at which the magnetic flux is increasing. It will not be perfect, usually. There is a situation if you're dealing with superconductivity, you can't have things hover because as it moves, it will constantly create a magnetic field to oppose they'll have competing magnetic fields, and you can get something to hover. Perhaps we'll go into more detail later on that one. So the big thing I want you to pull out of this is the direction wants to oppose the change in the magnetic flux.
The induced current.
The induced current will create its own magnetic field which opposes the change in the flux.
Okay.
Another way that we can look at this, get the exact same answer. As the wire moves this way, I can't get free energy. I can't get to the point where I just tap this and this wire here just gets faster and faster and faster. In other words, if I move the wire this way, I need a net force on it that way, opposing the motion. So if I think about my wire there, if this moves this way, I want a force to go in this direction, so that would be V and that would be F. Well, if I've got a magnetic field coming out,